Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Today's presentation is part of our series on the NGSS core ideas, and the focus today is on motion and stability, forces, and interactions. Our presenters are Alicia Alonzo and Alex Robinson. We also have Ted Willard online with us to provide some information about the standards and facilitate our Q&A. My name is Bryn Slate. I will be moderating the web seminar, and Jeff Lehman is here to provide technical support. And before we jump in, I did want to remind everyone about visiting the NSTA Learning Center, which is your online portal for teacher professional learning. And now we have over 11,100 resources in the Learning Center, with over 3,900 of those for free. So lots of stuff to check out in the Learning Center, and you can add your resources to your My Library so you can get to those anytime you have access to your computer and the internet. So very convenient for you to get to the Learning Center when you need it. We do have community forums that are a great place for you to connect with other science teachers and talk about content and pedagogical topics, including the NGSS. If you need help finding information, do reach out to our online advisors. They are always excited to help folks find what they're looking for and to help teachers get what they need. So reach out via that live support button. We also do have free tools that can help you organize your professional learning and to meet your goals. So check those out as well. Everything is available at learningcenter.nsta.org. And now I'd like to go ahead and introduce our presenters. As I mentioned, Ted Willard is our Director of NGSS at NSTA, and he'll be providing some introductory remarks as well as facilitating our Q&A today. And then our featured presenters are Alicia Alonzo from Michigan State University and Alex Robinson, who is a teacher in Middleville, Michigan. So we're excited to have them online with us, and I will turn it over to Ted to get things started.
Thanks, Bryn. Thanks, everyone, for being here tonight. Just to give you a quick little overview of the standards here to begin with, so we're all on the same page. Those of you who've seen these before are probably know this script pretty well. Standards were produced by 4 organizations: the National Academy of Sciences, Achieve, and the American Association for the Advancement of Science, and then my favorite, NSTA, obviously. There was sort of a two-step process of first developing the framework for K-12 science education and then developing the standards. And the standards are a guide for assessment, curricula, instruction, and teacher professional development. We'll start off with just sort of a closer look at the framework itself that was developed by the National Academies and was released in 2011. And the big key here is that promotes science education and promotes the idea that there are 3 dimensions to what standards need to focus on. There are scientific and engineering practices, cross-cutting concepts, and disciplinary core ideas. If you haven't had a chance to look at the framework, I would strongly suggest it be your first stop in understanding the standards. You can get a free PDF from the National Academies, or if you're the type of person who likes to have paper in hand, the NSTA Press Store has copies available as well. Here's some examples of what the practices are, and as we've mentioned before, we've done previous web seminars last fall on these practices. There's things like asking questions, planning and carrying out investigations, constructing explanations, and designing solutions. These are really what I think personally is the biggest thrust forward in science education and in the framework. Some of the most valuable pieces are these practices, and these are things that students engage in to really gain an understanding of content, and we'll talk a little bit more about that in a bit. The next piece are cross-cutting concepts, and these are ideas like cause and effect, systems, structure and function that aren't unique to any one particular discipline within the sciences. It's not just for life science or earth science or physical science, but really cut across all of those disciplines. And finally, we've got the disciplinary core ideas themselves. So life, earth, physical, which is where we are focusing on some things tonight, and engineering and technology has been, for the first time, sort of added to this mix in terms of thinking about the core ideas. Now, those core ideas get further broken down. So here in physical science, we've had web seminars on matter and its interactions, motion and stability, forces of interaction, which is where we are tonight, I'm sorry. Energy and waves we've done already as well. And each of these pieces, like force and interactions, it breaks down to some finer grained elements. So the framework spelled all of that out, but the standards then operationalized all of that. It took these pieces. And the standards themselves were developed by a coalition of 26 states, coordinated by Achieve. They're the states, again, that were involved in this. And a group of writers, 41 writers who spread around the United States. That map kind of captures where all of them were from. And at this point, we have 8 states that have adopted the standard so far. Washington, California, Kansas, Kentucky, Maryland, Delaware, Vermont, and Rhode Island. The states in yellow here have had some sort of official action either by the Board of Education or the State Department of Education looking towards the idea of adopting, but have not adopted yet. And obviously all states have the option to adopt. It's really a choice that states make in what they do with these standards. So here's an example of one of these standards. Develop molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in a chemical reaction. And so that statement is, as noted here, is what students need to be able to do at the end of instruction. They describe what is to be assessed. It's important to know that they're not specific directions to teachers about how they should teach in their class. But these performance expectations do blend together the 3 different domains here. So what we have is we can find the practice about develop models to support an explanation. We have content here, reactants and products, atoms and therefore mass are conserved in a chemical reaction. And we have this cross-cutting idea of matter being conserved in a chemical reaction. And so each of these elements combines together into that performance expectation. And so in looking at this, we really see how, as a guide, that looking towards instruction, we really want to see practices, core ideas, cross-cutting concepts, all blended together in a sort of a beautiful tapestry. So with that in mind, I'm going to pass things on over to Alicia and Alex, and for them to go into some depth now about force and motion. Pass it to you, Alex.
Hello. So we wanted to start by just giving an introduction to ourselves. So my name is Alicia Alonzo. I'm Associate Professor of Teacher Education at Michigan State University. The teaching that I do at Michigan State focuses on elementary science methods, and my research focuses on student thinking and how to support student thinking in K-12 science classrooms.
And my name is Alex Robinson. I'm a high school physics teacher over in Middleville, Michigan, small town in the middle of Michigan there. I teach AP Physics, Conceptual Physics, and 9th grade physics, and I also work with the VEX Robotics team in Science Olympiad and other extracurricular science activities. Right now, Alicia and I are working together in a curriculum project to figure out basically what's the best way that we can tap into students' intuitive ideas about physics, and especially forces and interactions.
So we wanted to get a sense for who you are, now that you have some sense for who we are. And our first question has to do with your roles. So are you a practicing teacher, a pre-service teacher, a curriculum specialist, informal educator, college and university instructor, or something else that we missed on our list?
And I'll just remind everybody that we'll be using our screen marking tools for this one. If you are on a mobile device, feel free to just type into the chat. But if you're on a regular computer, go ahead and grab that virtual pencil, which is on your screen marking toolbar right beside your participant window. And the pencil is the third button down. And I see that some of you are using that pointer too, which is just fine, except for if you do need to stamp in multiple rows, your pointer will travel with your mouse. So if you want to put a mark in multiple rows, go ahead and grab that pencil and put your mark up in the as many rows as you need to, since I know that some folks do play multiple roles in the education world. But this is great. It looks like we've got many classroom teachers joining us today, as well as some joining us from other categories. And thanks for typing there. Somebody's got some great handwriting for that virtual pencil. That's impressive. And folks typing in the chat as well. So great. Thanks, everybody, for giving us your feedback on that one. Alicia, do you want to make any comments on this one?
No, I think we'll just move on and find out sort of what level of schooling people are most associated with. So the next question is your focus grade level. So if you are a curriculum specialist in a district and you work at all of those levels, feel free to put that, or if you are a teacher, what grade you teach.
Well, great. Thanks, everyone, for giving us some feedback on this one as well. It looks like, again, we've got some in all of the categories. Looks like the middle school teachers or folks working with the middle school grade level band may be the majority here, but we definitely got across the grades, which will give us some great conversation as we dig into this core idea.
Yeah, so as we said, Alex is a high school teacher and I mostly do elementary methods, but I think the examples that we'll be giving will sort of be quite easy to adapt in terms of thinking about middle school. So in some sense, the middle school people have the best of both worlds in terms of being able to get multiple examples that could be applicable for them. So Ted gave a little bit of an introduction to the NGSS, and I feel like when I first started looking at this document, it seemed really, really overwhelming to me, and this big page with all these colors and things on it. And so I wanted to start by just sort of going over the structure of those pages so that we can sort of contextualize the rest of our conversation this evening. So before we do that, though, we wanted to get some sense for how comfortable you already feel with that colored page. And so if you could use your pull button to indicate your level of comfort with those pages of the NGSS.
Thanks, Alicia. And I'll just remind folks that your pull buttons are located right at the top of the participant window under your own name. You'll see the button there with an A on it. If you mouse over, you can pick A through D. So we'll give everyone a moment or two to read through the choices here and give us your best response. And do appreciate everyone jumping on this poll and giving our presenters some feedback on how familiar and how comfortable you feel as we jump into a little bit more about the NGSS. And I'll go ahead and close our poll in another 5 seconds so we can take a look at everyone's responses. It looks like most folks have had the opportunity to respond. So I'll go ahead and lock that poll and put up the total responses here, and I'll try to squeeze this in a place that doesn't block too much of our other text here. Maybe we'll just overlap our question a little bit. And I'll turn it back over to you, Alicia, to discuss these results.
Great. So it looks like quite a few people have been attending the other web seminars and are feeling quite comfortable with the NGSS. I want to make sure that those who are less comfortable have a chance to sort of orient themselves. So I'll go through the slides somewhat quickly, but hopefully that'll give everyone sort of a starting point for what we're going to be talking about today. So at the top of the page is the performance expectations. And this is an example from 3rd grade. I picked it in part because it's shorter and it'll fit better on the slide. These are statements about what students are supposed to be able to do as a result of instruction. So as Ted was emphasizing, this isn't a list of instructional activities or things that are necessarily supposed to happen in the classroom, but rather things that students should be able to do at the end of instruction. The colored boxes below unpack these performance expectations, showing the content that students should understand and the practices that they should be able to engage in order to meet the performance expectations. So the performance expectations are crossing particular content and practices, but students should have the opportunity to engage with other combinations of content and practices as part of instruction. So these are an example in some sense of what the content and practices look like together, but the idea is to be thinking about how different combinations could be made. I wanted to look just a little more detail at one of the performance expectations. So this is a statement, again, of what students should be able to do to demonstrate their understanding. So in this case, plan and conduct an investigation to provide evidence of the effects of balanced and unbalanced forces on the motion of an object. So that's fairly straightforward, but then there's these extra clarification statements here and the assessment boundary here. And I want to spend a little bit of time talking about what those are. So the clarification statement gives some idea of what are the types of situations in which students might demonstrate their understanding. Another way to think about this is it gives examples of the phenomena that are relevant to that performance expectation. So it can give some ideas of the kinds of things that students might be doing in a classroom situation. The assessment boundary is sort of giving some sense for what's fair game in the assessment. So in this performance expectation, for example, students are only expected to consider one variable at a time, and they're supposed to think about force qualitatively as opposed to quantitatively. So as I mentioned, the performance expectations cross practices, content, and then there's also the cross-cutting concepts. And the blue box is for those science and engineering practices. And these boxes describe what practices are involved in the performance expectations at the top of the page. And the text in the blue box provides a little bit more detailed description of the components of the practices that are included. So for example here, the planning and carrying out investigations involves applying the idea of a fair test and collecting data to serve as evidence. The blue boxes also contain some connections to the nature of science down here. The disciplinary core ideas are the orange, and this is the content that's included in the performance expectations at the top of the page. It's important to note here that the disciplinary core idea is motion and stability, forces, and interactions. And what are listed here are components of that disciplinary core idea that students should be engaging with at a particular grade level. So for example, you can see here that one of the pieces that students should understand at third grade is the idea that forces have both strength and direction. The green box has the cross-cutting concepts, and these are overarching ideas that cut across life, physical, and earth sciences. So for example, students work with patterns of motion in the forces and interactions section, supports their understanding of patterns being used to make predictions. There's also connections here to engineering, technology, and applications of science. This is a way to think about how the engineering practices might cut across some of the concepts from the engineering practices might cut across some of the content that students will be engaging with. There's also a section at the bottom of each page that has connections. These are really useful in terms of cross-grade planning and for cross-subject planning, either in elementary classrooms or as a school-wide effort in middle or high school. So the first set of connections is to disciplinary core ideas at the same grade level. There aren't any here for third grade, but for middle and high school, the force and interactions disciplinary core idea is connected to the disciplinary core idea of energy. Next, there are connections to disciplinary core ideas at other grade levels. This helps to illustrate how ideas build throughout the NGSS, and we'll look more at the progression for forces and interactions later this evening, but this is a good way to check if you're teaching at third grade what students are learning about forces and interactions in kindergarten and then what they will be learning in middle school, for example. The third set of connections is to the Common Core standards for English language arts and literacy. And again, this may be particularly useful for elementary teachers, but thinking about school-wide efforts to support students in the Common Core standards, this is a way that you can start to make connections in science. And then finally, there's connections to the Mathematics Common Core standards. For example, there's connections to the math standards having to do with measurement for third graders. So our focus for today is going to be on the practices and the disciplinary core ideas. And the reason I want to focus there is because, again, we don't want to be teaching students directly the performance expectations, but rather to be thinking about ways to cross the content and practices together. And so we're going to focus on those two things that in planning instruction would be combined together. So I just want to start by sort of overviewing where we're going in terms of the science and engineering practices that we'll be covering and the content that we'll be covering this evening. So this is a list of the science and engineering practices. Ted showed you the same slide earlier. And we're going to be focusing in particular on the ones sort of in the middle. These are the ones that are included in the performance expectations for force and interactions. And they range from planning and carrying out investigations to using mathematics and computational thinking, constructing explanations or designing solutions, and engaging in argument from evidence. So this is a set of practices that students are expected to be developing understanding of and engaging in throughout instruction on force and interactions. In terms of the content, again, there's disciplinary core ideas for physical sciences, life sciences, earth and space sciences, and engineering, technology, and applications of science. And we're focusing on the physical sciences. The second one down is motion and stability, forces and interactions. And then within that, there's three components. One is force and motion, the other is types of interactions, and the third one is stability and instability in physical systems. The first two are really emphasized in the NGSS, and so we're going to focus most of our attention there this evening. Another way to think about the content that we'll be going over this evening is that there's sort of a grid, in that there's one part that has to do with the relationship between force and other physical quantities. So this is what we usually think about when we think about the relationship between force and motion, Newton's law, F equals ma. But this also includes things like Coulomb's law that help us to think about the forces involved in electrical interactions. The second piece is the idea of forces as interactions. You might know of this as Newton's third law. This is the other sort of big idea that's part of these two parts of the disciplinary core idea. And within that, students are applying these ideas to two different types of forces. So there's contact forces, which you might think of as pushes or pulls, and then non-contact forces or field forces such as gravity and magnetic fields, electric fields. So this is sort of a map of the content that we'll be covering tonight, and we're going to start with that first idea. So this is the disciplinary core idea, part one. We'll be starting right here, and I'm going to pause now to see if there's any questions before we move on.
Sorry, forgot to hit the button. So if you have some questions for Alicia or Alex, put a note in here. Put a note in the chat, and we will try to go through it. And I'm doing a little bit of wait time here. I want to tell you, Alicia, I really love your little diagram that has the sort of the colored box down at the bottom with different areas to highlight. Dwayne asks if each of the quadrants in your previous diagram are equally significant.
So that's a good question. I would say that in terms of the emphasis in the NGSS, that first one is probably covered more. The forces and interactions come in more in the later grades, and it's part of all of the standards as we'll go over later, but I think the real focus is on that first part, and that's where we'll be spending the bulk of our time this evening.
Great, I think Dwayne was happy with that answer. Chuck's got one quick question here. Are all forces really field forces, even contact forces, due to repulsion of fields since atoms are mostly empty space? I think that's what he's pointing to here. And I think this is a great point to sort of talk about, different levels of understanding.
This is Alex. I'll go ahead and take that one. This is funny because it's something I actually talk about with my students. Actually, yes, all the forces that we see are one of four forces. The electromagnetic force, the gravitational force, the nuclear weak force or the nuclear strong force. And so most of the contact forces that we see day to day actually have more to do with that electromagnetic interaction between the atoms. And you can kind of think of it like an atom is a positive something surrounded by a whole cloud of negative somethings. And the things that get close are those negative somethings, and they kind of repel each other as they get closer, and that strength gets stronger and stronger, and that's kind of what we perceive as contact. Now, that kind of blows kids' minds, so I'm not sure how much you want to go into that idea, but it is certainly something that gets their brains thinking.
Yeah, thanks very much. Why don't we go ahead now and continue? I like that last comment you made in particular of finding the right times to bring kids' minds to that so we don't leave brains scattered all over the place after we blow their minds up. Great. So let's move on. And
okay, so we're starting off now with those that first disciplinary core idea, this idea that force has something to do with motion. So I've got a quick poll for you, and I just want you to see, first, if you think you know how your students will think, answer as your students. If you aren't sure how your students will think, then feel free to answer as yourself as well. So the question is, Derek throws a stone straight up into the air. It leaves his hand going up through point A, gets as high as point B, and then comes back down to A again. Ignoring air resistance, what force or forces are acting on the stone when it's moving up through point A? So this is as it's being thrown up.
Okay, everybody, and your poll buttons are available for you at the top of your participant window. You'll see the button with the A on it, and as you take a moment to think through this question, we'll give a few moments here to give everyone a chance to respond, and appreciate you submitting your answer there on our poll buttons. And it looks like we've got about half of our participants have submitted an answer. Thanks for that. Alex, let me know if you want me to put up the graph. Did you want to see all the answers or just discuss from here?
I think it's important to see where the thinking is, so go ahead and throw it up there real quick.
Okay, sure. Here we go. I'll go ahead and lock the poll, and here is our graph.
So the thing that I noticed here is that most either people have the idea or see that their students would have the idea that both the force of gravity and Derek's force are acting on the ball as it goes up through point A. And that's one of the things that we want to talk about today and really clarify in terms of how we can address this type of idea with students. Okay, so disciplinary core idea 1, and we'll go back to that poll again in a moment. So disciplinary core idea 1 deals with this idea that unbalanced forces cause changes in motion. Contact forces, pushes or pulls, the ones that we normally talk about in physics, deal with when two objects are in contact, whereas field forces happen even when two objects aren't in contact. One idea that's really important is that these forces are there when two objects are interacting, even if they aren't in contact. So we'll talk about that a little bit later. Okay, so where does this idea come from that essentially as this ball goes up, gravity's working on it, as well as the force from Derek throwing it up? So in our everyday experiences, we see that forces cause motion and that a force is usually required to keep something moving. Now, as science people and as a physics teacher, I think about forces in my favorite land, physics world, where everything's magical, right? And you push on something, and the box speeds up as you push on it, and then you stop pushing. Oh, you stop pushing, and that box just keeps moving and moving and moving forever and ever. Once there isn't a net force acting on it, it keeps moving on forever. But that's not the intuition. That's not the idea that students enter my classroom with. In their experience, when they push on something, friction is also acting on that object. So they can push on something and move at a constant speed across the floor, and when they stop pushing on it, friction slows that box down to a stop. So in everyday experience, what students are seeing is this idea that a force causes motion, and when I stop applying the force runs out, and the box comes to a stop. Okay. So what we expect students to see because of this intuition, because of this idea they come in with, is most students do have this idea that gravity is acting on the object as it's coming down. Obviously, what goes up must come down. Gravity pulls the ball down. But they also feel like Derek's throw still is affecting that ball as it goes up, almost as if the force follows along with the ball. In reality, is what we hope the students get is that once Derek is done interacting with that object, he no longer has any effect on that object. There is no more force because there is no interaction. So now only gravity is actually acting on the ball as it flies up through point A towards point B. And this is really ultimately where we want our students to be in the end.
So we want to talk a little bit about how this idea builds from K to 12. I think the really interesting thing about this disciplinary core idea is that it's really the same idea starting in kindergarten and moving all the way through high school. So this idea that forces cause changes in motion. I think, as Alex was saying, students often think that forces cause motion, and what we want to move them towards is this idea that forces cause changes in motion. As you move from kindergarten up through high school, there's increasingly precise and mathematical expressions of the relationship between forces and motion, but that relationship itself is staying the same. There's also extensions to forces other than pushes and pulls, so students start learning about magnetic forces and electric forces, but again, that basic relationship remains the same. So in kindergarten, we use the language of pushes and pulls, so students aren't talking about forces yet. But you'll see that they're thinking about forces already in terms of strength and direction. And they think about those forces causing or pushes and pulls causing changes in speed or direction. So again, in order to think about changes in motion, students need to be thinking about both speed and direction. In kindergarten, we typically talk about causing motion, or we say, oh, we started the ball, we stopped the ball, but really emphasizing the starting and stopping as being a change will lay the foundation for further learning in later grades. So in third grade, students do start talking about force, and they're talking about force in terms of having more than one force acting on an object. So they begin to think about forces that could be acting so that an object is staying still if there's balanced forces. They also start thinking about changes in speed or direction if the total forces that are acting on an object are non-zero. At middle school, they add more details. So they start to think about the idea that mass is involved in the effect that a force has on motion. They also start thinking about a reference frame and units of size so that you can't describe the position or the direction of an object without knowing the reference frame, without knowing the units. In high school, this gets sort of formalized in terms of Newton's second law, so it's becoming more mathematical. And we also introduce the idea of momentum and conservation of momentum as a way of understanding the changes that are occurring when a force is applied. The other change that happens is that there's different forces that are introduced. So again, in kindergarten, we talk about pushes and pulls. From third grade on, we talk about force. In third grade, also, students get introduced to the idea of electric force, magnetic force. We haven't talked too much about fifth grade because there's only one performance expectation at fifth grade, and it has to do with gravitational force, and that idea carries through middle school and high school. So we want to stop here and see if there's any questions about this disciplinary core idea part one before we give you some instructional examples.
So I'm going to start with people. I've asked people to post some questions so they've got them. I'm going to start with a question that comes to my mind, and I even say this as a former physics teacher. I would have thought that gravity would be something that they would deal with before or around the same time that they would deal with electric or magnetic forces, because it's something that they tend to have an experience with. And I'm curious if either of you know or have considerations about why that happens later in the whole sequence.
So gravity is mentioned in third grade as an example of a force, so it's not that it's being ignored. I think in part it ties into some of the other earth and space science performance expectations that come around 4th grade. So there's connections across physical science and earth science, and then also connections in the grade level. So I think it's partly a matter of just where the content makes sense in terms of other ideas that students are learning about at the same time.
That makes sense. So first, Luann here has this question about, is gravity a field force?
Yes, gravity is a field force because it's a force that doesn't need direct contact. And the way you can think about that is if you jump off the ground, right, what pulls you back down is the interaction in this gravitational field between your mass and the mass of the Earth. And so as you jump up off the Earth, even though you aren't in contact with the Earth anymore, the Earth still pulls you back down. So that's why we consider it a field force. The same thing for magnetic field, the same thing for the electrical field, because all those forces are able to create an interaction between two objects without direct contact.
Great. And then Georgia asks here, when is it appropriate to start discussing forces as interactions between two objects?
We are going to get to that. That is part of the second part of the disciplinary core idea. And as you'll see, as beginning with kindergarten, there's some idea of forces as being interactions. And I think that's important, again, for building that foundation for later understanding.
Great. Elaine here has this question, is momentum a force?
You double-clicked. Oh, okay, there we go. Sorry, I thought we double-clicked to talk about it. No, momentum isn't a force, and this is actually one of the reasons why we need to think about forces as an interaction at such a young age, because students know, children know that when an object's moving, you know, bigger objects are harder to stop, faster objects are harder to stop. But momentum isn't a force. Momentum is a totally different quantity. It's an expression of how much motion there is in that system or how much motion that object has. Whereas a force only describes an interaction between two objects. An interaction isn't something that's carried on with an object after those two things are stopped interacting, if that makes sense. If I push something to get it to move, I'm only actually applying a force as I'm in contact, as I'm interacting with that object. When I stop interacting, the result of that force, which is momentum, the fact that it's moving, will continue on, but the force itself doesn't.
Great. So I'm going to just touch on one more question here, but I'm going to give you a chance to hold off on it if you want to. Rachel, I think that's an interesting piece here. She's talked about that she's just experienced her first 9 weeks as an 8th grade science teacher, and that her students can understand some concepts about motions. The calculations are really bogging them down. And do you have any suggestions for how to deal with that, other than just having them do it again and again? And if you've got some pieces that touch on this more later, I think that's fine to deflect it if you'd like to.
I mean, just a small piece. One of the things that I really try and emphasize in my class, at least, and I teach high school, and they're still having problems with the math, let me tell you. One of the things that I try and emphasize is that part of the math is understanding how mass, how acceleration, and how force, how these quantities interact with each other. So I try and emphasize that I give points and I give credit for good thinking about forces. So even if they aren't able to work out the numbers, they can still make comparisons in written language and say, this object has a large mass and experiences a small force, so it will have a relatively small acceleration. Even if they can't come up with a number, I still try and give them some credit for answers like that, just so that way they're still thinking about it conceptually.
Another important thing to note is that in the next generation science standards, at 8th grade, it's still pretty qualitative. And so there's an opportunity to develop those conceptual understandings before the math sort of gets layered on in high school. So I think really focusing on students' understanding of the relationship without the math is actually going to serve them in the long run.
Great. I think that makes perfect sense to me. Why don't we go on here, and we will come back to some questions in a little bit.
Okay, so one of the things that really got me when I started looking over the NGSS is basically the purpose of labs and the purpose of activities and kind of what's the point of doing these hands-on things. So I just want to do a quick poll and see, why do you normally do a lab? Why do you normally do a lab? So to introduce a new concept, to reinforce understandings of a concept through an application in the real world, to allow students to discover scientific ideas for themselves, to provide opportunities for them to engage in science and engineering practices, or just for variety, just to mix things up with the students.
Okay, great. Well, thanks, Alex, and thanks everyone who have already jumped on the poll and submitted their response. And I see that a number of you are saying that you would prefer to pick multiple. Go ahead and select probably, if you can, the top reason for you, with the understanding, of course, that we know that multiple people are doing labs for several reasons, but feel free to pick your top reason, and we'll put that into our count here. So great, thanks for everybody who's responded so far. Looks like most folks have gotten an answer in there, and in addition to our chat comments. So we'll go ahead and lock what we have and put up our graph so everyone can take a look.
Excellent. Okay, so is what I found is that I too thought of a lot of different reasons for doing labs, and as I was looking at kind of my purposes for doing the labs, to reinforce understandings, to allow students to discover these ideas, as I'm looking at how I do these labs, I don't think that I was always getting to the goal. And one of the things that the Next Generation Science Standards really want you to do is to have these students use the science to engage in engineering practices, so to create something new with their understanding through a lab experience. So reevaluating kind of like what my labs looked like in the past and what a lot of other labs look like, lots of ones I've seen online and gone over. How do we incorporate science practices into them? So first, start off with like the old lab. So the way that I traditionally had done labs in the past is I'd find a really good lab either online, or I'd develop one or work with a colleague, and we'd come up with a lab that gives a set of instructions like use a spring scale to pull a book across the floor, use the smallest force in order to get it to move. Every 3 seconds, mark the book's location, and then repeat it for increasing amounts of force on the spring scale. And so we would talk about the relationship between force and acceleration, but that question seemed to be independent in the student's mind, independent of what they were actually doing in the lab. So we would talk about this idea of relationship between force and acceleration, and then I would give them this lab that I or somebody else thought up to work on. And when we all got said and done, we maybe had a good discussion or two, but I don't think it was as good of an experience for them as what it could have been, because I'm not sure they fully understood the lab. They were just kind of buying into whatever I was giving them. So NGSS, I think, does a nice job of looking at incorporating students' ideas into labs. So instead of just starting off with, here's your lab procedure, here's what you need to do, and these are the results you should come up with, fill in the blanks and make sure to get me the right answer when you're done. Instead, what I've been doing since I've been getting into the NGSS stuff is looking at how do I make a lab a discussion with my classroom before we pull out a spring scale, before we pull out any of the instruments. So I kind of, with my classes, do like a gradual release. We start off together discussing some questions like the ones up on the screen. So if we're discussing how does a constant force affect an object's motion, then we're going to ask questions with the class and discuss with the class, what are we going to change, what are we going to stay constant in order to see a relationship between force and motion? What type of data do we need to collect? Do we need to collect position data, speed data, time data, force data? How are we going to collect the data, make sure that we have some form of consistency, or at least make sure that the data is valid, and then how much data needs to be collected. This puts students in on the ground the ground floor in terms of figuring out, like, not just how do I do the lab, but why am I doing the lab, and how do I make it the best lab that I possibly can. This way we aren't just critiquing what are the numbers that you got out of the lab, but critiquing the entire lab in general for its authenticity and what it actually shows. Another thing you can talk about is how are we going to show this idea? If you look at the title there, Analyzing and Interpreting Data, is one of the things NGSS asks us to do as a practice. So what's an appropriate way of showing evidence in such a way that we can see a relationship between position and motion and force? I don't know if, about you guys, but I cringe every time I see a bar graph that's supposed to show a relationship between one thing and another, because those are rarely something that makes sense. So we can have a discussion about data, and I just kind of sketched out a couple different things that you might see looking at what types of student data might come back. Okay. Another advantage of looking at different forms of data and discussing it with the class is, depending on your class level and depending on where you're at with the students, different forms of data can give us a whole lot of different means for interpreting that data. It shows a lot of different things. So like with my AP students with high ability in math, we might look at the force versus acceleration graph right here and talk about, okay, what does the slope of the line mean? What does the y-intercept mean? Looking at this idea that, wait a minute, when the force is at this amount, the object isn't accelerating at all, right? So why is that? And we can get in discussions about, well, because friction. That's the point where the force is going to balance out friction. But we can also do that with like a strobe representation of the forces and look at, okay, at 5 newtons I seem to get a constant speed, but as I go to 8 newtons, the position gets further and further apart with each second, and at 10 newtons, it gets even further with each step. So looking at this idea that at 5 newtons, it seems the force is that the motion is at this constant speed, but as I start to increase the force after that, now we're starting to see acceleration. So what's special about that 5 Newton force? And again, looking at this disciplinary core idea and saying, that's where your force is going to balance with the force of kinetic friction. So you can see that different forms of data gives us different options for how we're going to discuss it as a class. Not just us, but also how our students are going to discuss and critique the data. In the end, we're using, and I talked about this a little bit on the last slide, I have a tendency of getting ahead of myself. So using the data as evidence and providing an argument for what is the relationship. So when we do this as a class, or when we bring all this information back together as a class, we can critique others' data and say, okay, how does this piece of data, how does the graph give me more information than the strobe, or vice versa? That way students are participating not only in analysis of their own data in lab, but also in analysis of the class data in lab.
So one thing I want to point out about this slide is that we've had at the bottom of all of them this idea of engaging an argument from evidence, and we usually think about that as being a claim that we're making about our data, but we can also think about it in terms of making claims about the way that we've set up our lab or the way that we're analyzing our data, what data we need. And I think the NGSS does a really nice job of laying out many different types of arguments that are entailed in that scientific practice. You'll also see that communicating information, even though it's not explicitly part of the performance expectations for force and interactions, is included in many of these things. All of the discussions that Alex was just talking about involve students communicating their ideas. Before we move on to talk about the difference between what this lab might look like with younger students, I wanted to point out that you could think about having all of these discussions either, with an AP class, maybe you do all of them. Maybe if for a middle school class or for another class in high school, you might decide to focus just on one of them. So to say, okay, today we're really going to focus in on how to plan an investigation, and that's going to be the focus. You'll provide students with more information about how to analyze the data so that you can focus on one of the practices. So it's flexible in the sense of thinking about how many of the practices you want to engage students with at any given time.
I think, too, one of the things that that we don't have time to obviously go through all of this, every single lab with every single class. But you can, like I said before, you can kind of gradually release this. Start off talking about this with an entire class, and hopefully by the end of the year, your students can get to a point where they're having these discussions amongst themselves in the lab group, and these arguments are evident in whatever writing they're presenting about the lab report when it's all said and done. So don't feel like this needs to be something where you're taking all this time in class to do these long discussions. That might be how it starts, but we've got to model that before we can expect them to do it on their own.
The other piece I think of modeling that's really important to do is this idea of critique. So we often put forth an argument, but then don't engage students in thinking about where the flaws are in that argument or how they might improve something, and that's another important piece of the NGSS. So thinking about what this would look like for younger children, sort of following along with the way that we saw the ideas progressing from kindergarten up through high school, we would expect younger students to be able to engage with less precise measurements. So, for example, we could think about kindergarten students talking about a push being a hard push or a light push, whereas the high school students might actually be measuring a force with a spring scale. We could also think about descriptions of motion. So an elementary school student might talk about the motion being fast or slow, starting or stopping, or making comparisons like this is faster or slower. Middle school students might be expected to start thinking about average speed by calculating distance over time. And then as Alex showed, high school students could be expected to think about more sophisticated measurements in terms of how do we look at position and time and how does that tell us about acceleration. Another key difference has to do with this idea of whether the relationships that students are dealing with are qualitative or quantitative. So an elementary school student, for example, might make a statement like, if I push harder, I cause a bigger change in the motion of this truck. But middle school students could still be working with qualitative relationships, but they're beginning to consider additional variables. So they could be thinking about, well, if I push this truck at a certain amount, what happens? Or I apply this force to a truck, but this one's much heavier, what happens? So they can start to think even though qualitatively in a more complex way than the younger students. And then at high school, there is sort of this expectation that students would be able to work with a formula, which involves them being able to manipulate that formula to calculate different things.
So going on with that last idea of, or what we talked about in the poll before, this idea that NGSS wants us to do something a little bit different, not just to come up with conclusions about the physical world, but then to use these conclusions to develop solutions, to design solutions to problems, which really gets into how do we incorporate engineering practices. So how do we adapt these old labs so that way we can actually look at some engineering practices. So again, kind of a comparison, because one of the things that you can do, you don't have to, recreate the wheel, you just have to tweak it a little bit. The old lab that I might have done before, and that I know is done, K through 8 in various classrooms, is how many loops of wire wrapped around a nail or something like that, how do those affect the magnetic field? How do they create a stronger electromagnet? Now, before, when we did the lab, it may have been like looking for the right answer. If I add twice as many loops, it makes an electromagnet that's twice as strong. So at the very end, the kids are saying, okay, so what? So I could have told you that, and you probably would have believed it. So the new lab design, the way that I would do this differently, thinking about NGSS, I might, instead of having the purpose is determine how many loops wrapped around an electromagnet affect the magnetic field, I might instead say, design for me the most cost-effective electromagnet that has the capability of lifting a mass of 4 paper clips. So the application is, basically the application is the ultimate goal. Instead of just looking for the relationship, it's looking for what are the relationships that exist and how do I balance those relationships with costs to create the best electromagnet to solve my problem. So planning and carrying out the investigation, again, you can have these conversations with students similar to the last lab. So what factors affect the strength of the electromagnet? What factors do we need to take into account to basically solve the problem? So some samples might be like looking at how big is the core? If I put different sized nails in the middle of these wire loops? How big is the current going through? You could do this by, I've got a setup here looking at the resistance for changing the amount of current. You could do it with how many batteries. Just get a different battery holders, right? One that holds 2, one that holds 4, one that holds 6, one that holds 8. You can pick them up at Radio Shack. Or how many wire loops do you have? How does that affect the strength of the electromagnet? So again, in order to answer the question, we need to figure out what data needs to be collected, how we're going to collect it, and how much data in order to get accurate results from it. So again, instead of just giving them the problem and saying, here's a problem, here's the obvious way of solving it, now go and do it and fill out the answers that you know, instead we're saying, this is the design problem you're dealing with. You're going to have to now balance a bunch of different ideas and figure out what's the best way to make the electromagnet. So some of the different, and again, these are just sketches of perhaps some of the different visual aids students might come up with, looking at what is the core of the electromagnet made of. If there's 20 turns, how many paper clips does it pick up? How many paper clips does it pick up based on the number of turns around the electromagnet? Or maybe even like how many paper clips does it pick up if I have 20 turns again, but I change the number of batteries? So again, we're looking at what factors increase the strength of my electromagnet. So what should we consider in the design? Which ones have large effects? Which ones have small effects on the magnitude of the electrical field there? So then when they design the solution, another part is looking at obtaining and communicating information. So when they actually go to design this most cost-effective electromagnet, we can look and say, okay, I know what it takes by changing these different variables to lift 4 paper clips. Each student can do each lab, or you can split it up based on having different groups judging different things. How do you get the most cost-effective electromagnet? One of the things that they're going to need to do is look at what types of costs do we deal with? What types of costs do we deal with for what's the expense of the wire? What's the how does the cost of the nail relate to the thickness of the nail? What's the difference between a tube that's 3 millimeters thick that's made of plastic and a metal piece that's made of iron that's 3 millimeters thick, right? So again, now they're starting to look at cost, and instead of just saying, to make the best electromagnet, I have to wrap tons and tons and tons of wire around it, instead they're saying, well, I don't want to add too much wire because that might be a more expensive way to go. I might instead want to change what the core is made of. So you see that they're dealing with designing based on these different constraints rather than just trying to say, okay, the best one's made by having the most loops of wire. There's a design solution there. You might even provide the students with, if you don't have internet access where they can look up the information, you might instead provide them with a cheat sheet that gives them the cost of different materials based on length, based on the diameter, based on the material. So you can give them that cheat sheet, and then it's up to them to read that and figure out, how do I take this information and solve my problems? So we wanted to take a minute to see what questions you have.
And as usual, if you've got some questions here for Alicia and Alex, post them up on the board and we'll put them up. I think I've got to see a few people already. So I think there's a nice sort of fundamental question that Christy has brought up. I mean, I think ties into some of the things that I saw going on in the conversation earlier. How do you get kids to think this way? What are some tactics to create this sort of culture in your classroom?
For me, I think that the biggest difference has been actually having a conversation and be willing to step back and not give the right answer. Students are so uncomfortable with whether or not they have the right or the wrong answer, and I think when they work together to come up with an idea for how do I solve this problem, it leads to a better environment. That being said, they aren't going to do it on their own. So part of what you need to do in the beginning is model. How do we have a discussion? So when they come up with 25 ideas, how do I critique those ideas and whittle them down to say, okay, maybe this idea, did you think of this idea? Did you think of that idea? So taking their ideas and then adding your own spin on them. So they're seeing how you think. Another thing is don't be afraid to be wrong. You know, you might be talking with your students and say something and then say, wait a minute, actually, what I just said, I don't think that would work, because show them that it's okay to be wrong and show them what it looks like for somebody who's done it before to think through a problem, struggle with the problem, and work through it and come up with a solution. So I think that's, at least for me and my students, that was the biggest thing, is just being willing to give up the control over the lab and have them make mistakes, and maybe have a lab that's not as fruitful in terms of the content that they end up with, but is very fruitful in terms of their practices for how do I actually perform a reasonable lab. Because keep in mind, even if the lab totally botches, you still have sample data you can give them. You can always say, okay, you did this lab, and we didn't take into account these 3 or 4 major errors that really gave you data that doesn't seem to make any sense. If somebody did the lab differently, taking into account these pieces of error, this is what the data might have looked like instead. So you can afterwards go through and kind of patch up the concepts after the fact, but then the core, those engineering practices they've started to become more comfortable with, and they don't feel like they're being punished for not getting the right answer. You're saying, hey, it's okay to make a lab that's bad as long as you learn from that, how do I make a lab that's better next time? And then after that, maybe even make a lab that's good.
Great. Sort of a question I think that follows up on that. Does this new approach, these new forms of doing labs, take more time? And Margaret's noting that she thinks her students would need a lot more prep in the beginning.
Absolutely. You know, I think anything that's worth doing is going to take a little bit of time at first, because remember, a lot of this thinking is not something students are used to. I know that when students come into my class, when I say lab time, they're like, okay, give me the sheet, show me the boxes to fill up, I'll be done in 10 minutes. And we want to get away from that idea. So you might spend a little more time. I know my first lab this year, we extended over, we basically used about 2 days of class time. It was half of one class, a full class, and then half of the next class discussing the ideas. But it was well worth it, because the next time we only used about a day and a half. And hopefully the next time this year it'll take even less time, because as students get more and more comfortable, the questions that you have to pose to them about critiquing their lab on the first day, they're going to start posing to each other on the next day. And eventually, you can just remove yourself from the situation. It's never going to be perfect, but I think it's really good in terms of teaching the engineering practices.
Great. We've got another piece here, Laura, sort of asking for your impression of how or whether the 5E model would work in this whole approach.
So I think the 5E model is a way of thinking about inquiry, and in some sense, the science practices are a way of thinking about the things that you do when you're doing inquiry. In some sense, though, I think the 5E model tends to be more in an order, whereas I think the science practices tend to be something that you can pull in at different times. So you notice that the idea of engaging in argument came in throughout. The idea of using mathematical and computational thinking, that comes in throughout. Considerations of data comes in both when you're planning and when you're thinking about analyzing the data. So I think in some ways it portrays doing science in a way that's more authentic to how scientists work, in the sense of using practices more flexibly in pursuit of understandings about the natural world.
Great, thanks, Alicia. I think that use them in my sort of approach. I sometimes think of them as, tools you've got on your tool belt, and you pull out the one you need or want when it seems appropriate to, and it's not necessarily a certain order that you have to use them in, but you've always got them there to use when you need to. So great. Why don't we move on to the next piece here, and do some more questions towards the end.
Okay, so we've been spending quite a bit of time on the first the first part of the disciplinary core idea, and we want to spend a little bit of time now on this idea of forces as interactions. You've probably heard of this as Newton's third law, and your students will come in saying for every action there's an equal and opposite reaction. They've heard it too, but we want to sort of talk about the conceptual underpinning of that and what it means in terms of working with students about these ideas.
Okay, so again, I've got another poll here for you, and like before, answer how you think your students would if you are comfortable with that, and if you don't know how they would, answer for yourself. So the idea is a car crashes head-on into a tree. Which statement best describes the forces involved? So A, the car exerts more force on the tree than the tree exerts on the car. B, the tree exerts more force on the car than the car exerts on the tree. C, the car exerts the same force on the tree as the tree exerts on the car. Or, without further information, it's not really possible to figure this out.
And thanks everybody for responding to this poll question. It looks like many of you have been able to put in a response, so we'll go ahead and give just about 5 more seconds for those who have not yet selected an answer to do so, and then we'll put up our graph of responses. So I'll go ahead and close that now, and here is our graph. I'll put it up here so we can see the question, and I'll turn it back over to you, Alex.
Thank you. So what I'm seeing here is a lot of you are very comfortable with this idea that there's the car exerts the same force on the tree as the tree exerts on the car. And as what we found through a lot of our research is that that this isn't necessarily the idea that a lot of students are having. So let's take a look at this disciplinary core idea a little bit more. So first, the idea of Newton's third law, the idea that when two things interact, there's this equal and opposite force. For every action, there's an equal and opposite reaction. One thing that happens a lot is students misunderstand Newton's third law as a cause and effect scenario, as opposed to a pair of forces acting on two separate objects. They might see, like, I apply a force to a ball, the reaction is, of course, the ball moves. And, philosophy and movies just add to this misconception. But in reality, forces are always there present because of an interaction between two objects. Object A can't exert a force on object B without object B exerting a force back on object A. Forces are a description of how much interaction there is between two objects. One object can't interact, A can't interact with B any more than B can interact with A, because fundamentally you're describing how much the two are interacting with each other. So looking back at this question again, some of the ideas that we see students have, one is that the idea that the car exerts more force on the tree than the tree exerts on the car. And the main reason that we found for this idea is that the car is moving fast. So again, if students have this idea from DCI 1 that forces cause motion, then of course something that's moving faster has more motion, has more force. Another idea students have is this idea that the tree exerts more force on the car than the car exerts on the tree. This is, again, because of the effect of the force. The effect of the force is the car gets damaged, it gets bent, it gets crumpled, right? But that's the result of the force. It's not the force itself. And then there's D, the classic, I give up. Without further information, it's just impossible. I just don't think there's a way to solve this. Not only do students who are confused answer with this, but also students who rely heavily on the math and say, oh, I don't know what the math and I don't know what the acceleration is, so how can I answer? Right? When in reality, C is what we're looking for, this idea that the car and the tree exert the exact same force on each other.
So just like the first part of the disciplinary core idea, this one builds from K to 12 and starts with the same idea that's being sort of repeated across the grade levels, but with increasingly precise descriptions and extensions from pushes and pulls to field forces. So it's very similar to the way that the first part built over time. So we can see even in kindergarten, students are expected to start thinking about the idea that when objects touch or collide, they're pushing on one another. So again, in kindergarten, we're using the idea of pushes and pulls instead of force, but this idea that there is something happening when objects are touching each other. In third grade, they actually start using the word force to think about what's happening when objects are in contact with each other. And then this idea about the electric and magnetic forces not requiring things to be in contact, but that there's still something going on there. In middle school, there's sort of more formal introduction of the Newton's third law idea, but then also the idea that forces that act at a distance can be explained by fields. So getting this idea that there is an interaction, but it happens even when two objects are not touching each other. And then in high school, again, more about the idea of the fields and then beginning to think about what are the actual causes of those fields. So in all the cases, students are expected to be thinking of forces as happening with pairs of objects, and I think it's important for that language to be consistent starting in kindergarten so that when students get to middle school and high school, that those ideas make sense to them and don't seem quite so foreign.
Okay, so one of the things about the NGSS that they look for is this idea of using mathematics and computational thinking. So not just using the math to say, oh, look, see, I told you, but actually using the math to think about a solution to the problem. So I know one of the things that I used to do when I talked about Newton's third law is I always did the whole, hey, trust me, the forces are equal, and let me show you why based on the mass and the acceleration being a very hard idea to understand in the first place. Is what I found is that students by rote could tell me, oh yeah, the forces are equal, just so long as it's a physics question, but in the real world that doesn't actually happen, right? So we come up with this problem where we're getting an explanation and we show that, yeah, it's true with the math, but it's more of a secondary, trust me, this idea is true, here's some math to back it up. Instead, is what we can do is use the math to come up with the idea that those forces are equal to each other. So students already know that there's a difference. If I have a large object run into a small object, that there's going to be a difference in how those two objects react because of their interaction. Most have this idea that, you know, the small object will go flying away, the large object won't move as much, right? That's the idea. And students have an intuitive knowledge about how motion is affected by mass. And so what we want to do is, what we can do is base our description on what their intuition already is about the mass and the action that happens because of the force that's applied to it. So there's a couple ways that you can do this problem. As you can see, I've got a red ball and a green ball. They're colliding with each other. After the collision, the green ball goes flying off the other direction, and the orange ball, sorry, I said red before, the orange ball slows down a little bit as momentum is transferred, as there's a force of interaction between them. So one way to look at this is, rather than saying, trust me, the forces are the same, you can use acceleration, which you've already studied at this point, the acceleration and the time that the objects are interacting, to figure out that the forces are the same. So if we look at the orange ball here at the example on the right, if I know the acceleration is change in speed over change in time, I can calculate the acceleration, change in speed over change in time, to find an acceleration of -2 meters per second squared. Depending on the level you're at, you might include the negative, you might not. Just a reminder, that's just a direction. Negative is really just a direction when we're doing this. Once we know the acceleration, then we can use Newton's second law to determine that the force is a -20 newtons. During the interaction, the force is mass times acceleration, 10 times -2. I can do the same thing for the green ball. Look at the difference in speed over the difference in velocity over the difference in time of the green ball. It goes from -5 to 5, right? So my total difference is 10 meters per second over the half of a second that these two things are interacting with each other. So emphasis can be put on the idea that those are changing speed only for the half a second that the objects are interacting. Again, I find the acceleration is 20 meters per second squared. At this point, students say, oh wait, that's supposed to be 2 meters per second squared, typo. So at this point, students would say, 2 meters per second squared, negative 2 meters per second squared, that seems funny. They have, oh wait, nope. Sorry, I'm getting ahead of myself. 20 meters per second squared is the acceleration. If I look down here at the forces, right, that object, oh, it looks like we've got a typo on this slide. So that was supposed to be a 1 kilogram object there that experiences this force of 20 newtons. So this is actually supposed to be a 1 kilogram object here. Apparently we have an error on this slide. Sorry about that. So the idea, regardless of the math, still the same idea of looking at how acceleration and mass can be used to show forces the same. If I look on to the next problem, you can do the same thing with momentum. Now, keep in mind, this is actually supposed to be a 1 kilogram object over here, a 1 kilogram object. So keep that in mind in these math, in this math problem. So if we're looking at change in momentum, right, we can again look at the change in speed, right, therefore the change in momentum. So if I go from 5 to 4 meters per second, right, 5 minus 4 is 1 times 10, or 4 minus 5 times 10 gives me negative 10 kilogram meters per second as my change in momentum, as my impulse. If I know force is impulse times time, right, or force is impulse over time, or excuse me, impulse is force times time, or force is impulse over time, then I've got my impulse, my change in momentum, over half a second. I've got 20 newtons of force. Again, I come over to the other side, right? I look at the change in momentum of that object from negative 5 to 5 times the mass, 1 kilogram. I end up with 10 kilogram meters per second. So this is a neat opportunity in momentum. One of the reasons why I do this in momentum, I actually do the curriculum a little bit different where we do momentum before forces. And in this spot, you can see that both objects experience the same change in momentum. As a result, they also experience the same force since that change in momentum happens over the same amount of time while those objects are interacting. Now, I wanted to do this example just to show you that NGSS, everything doesn't have to be a lab, and I think that's something that we science teachers tend to, when we see the NGSS, we're like, oh, how can we do all these labs? Everything doesn't have to be a lab. You can do this computational thinking as well. So if you wanted to do it a lab, though, you could use something like air tracks, right, to look at the position versus time and the velocity versus time. So you could use an air track and look at what's happening to the forces while they're interacting, what's happening to the change in speed during the time that they're interacting. You could also do, one thing that I'm going to do with my class is using air pucks in 2 concentric circles. So looking at, we can calculate if we shoot an air puck at 1 at rest, we can calculate the speed as it crosses over this line to this line. The whole class can be in on this, calculating or measuring the time and calculating the speed as it approaches the second air puck. After the collision, they're going to go off in different directions, and we can calculate the speed after the collision. Again, another great 2-dimensional momentum problem, or if I have a good aim, 1-dimensional momentum problem. So what other questions do you have?
So we'll take just a minute here or so for some questions. I think people have been finding interesting pieces. I think one question that's come up here, Alex, is some of the math that you're doing here. I think everyone's in agreement. We know that it's not for elementary school students, but some questions about to what extent would you do some things like this in middle school versus high school, and at what level in high school?
Level-wise in high school, I think this is something that you could start off almost as early as like the freshman year. I know this is something that all of my Science 9 kids, my 9th grade science kids would struggle with this type of math. It would at least get some of those students, the leaders in the classroom in terms of understanding the concepts. It would get some of those comfortable with math to understand the concepts, and their buy-in is gonna end up working as they explain the same idea to the other students who are struggling with it. In terms of elementary stuff, I'm going to pass that over to Alicia.
I would say even middle school and then in elementary as well, the NGSS really has a very qualitative perspective, but that doesn't mean that you can't engage in mathematical thinking. So some of the reasoning about what happens when one thing increases and something else decreases are things that you can definitely talk about with elementary students, but a lot of the math that Alex was showing, for example, with momentum, that idea doesn't get introduced until high school, and the mathematical calculations are really not until high school, but you can build on that thinking in terms of thinking qualitatively about relationships in terms of how changing one thing changes something else.
So again, this idea of, the orange ball the big orange ball slows down a little bit, and the green one now is moving in that direction, very, faster or something like that comes into play here. That makes sense to me. Great. We're going to go ahead, I think, at this point, and I sort of I'm going to go over a few things in terms of other resources here at NSTA, and get people to have a chance to then fill out their evaluations of the course. But Alicia and Alex will stick around here, and if some folks have some other questions after that, we can post them. They can go ahead and start posting them now, and we'll answer them once we've reached that point. So with that in mind, just want to keep in mind that you can find the standards at nextgenscience.org, or you can find you can also find the standards on the NSTA website, and a lot of other resources at nsta.org/NGSS. And that there's a lot of opportunities here to connect and collaborate, both in terms of a discussion forum in the Learning Center at NSTA, and the NSTA has a member-only listserv on NGSS. So questions and the comments you've been having tonight, you've got some opportunities to continue those going on in those areas. We now are closing up tonight our discussion of physical science that we've been doing the last few weeks. You can find the archives for that. And starting 2 weeks from today, we'll be moving into the Earth and Space Science area, and would encourage you to come back and join us, or if you know folks who are interested in teaching in the Earth Sciences, and please let them know about these. And as pointed out, Life Science and Engineering coming after the first of the year. We've got numbers of web seminars on different topics we've been doing throughout, and you can find the archives, as well as we have a number of journal articles on different topics in NGSS that I would strongly recommend for you. Our next online short course is Connecting Science to Common Core with Picture Perfect Science Lessons, and Emily Morgan, author of those, will be doing that. You can get login information or register information at that link. And I want to point out, sort of hot off the press, is Roger Bybee's Translating NGSS for Classroom Instruction. I just got a copy in the last week. That is one of many books we have at the bookstore focusing on NGSS, and we encourage you to find those as your guides. We've worked with Mastery Connect to develop an app for NGSS, so you can always have at your fingertips the standards, and you can go find the information for that at our website. And I hope some of you guys will be out in Portland later this week. I'm flying out there tomorrow for our conference. We've got a number of different sessions and other conferences coming around throughout the rest of the year. And with that, I just want to thank you all for attending tonight. Thank Alicia and Alex. And we'll pause here and pass things to Bryn to deal with the evaluations.
Thanks a lot, Ted. And I also wanted to thank our presenters, Alicia and Alex, for a fantastic presentation today. And thank you to you as well, Ted, for providing the information on our standards. Appreciate that. Also wanted to thank the sponsor of today's web seminar, the Carnegie Corporation of New York. Thank you as well to the administration of NSTA for their support for web seminars. And a quick look at what's coming up on the web seminar calendar. Join us on October 23rd for Distance Rate Time Problems, Smart Skies, and then learn more about the NSTA Learning Center on the 29th of October, and come back for more NASA Explorer Schools on the 30th for Pythagorean Theorem. And you can register for these programs and more by going to learningcenter.nsta.org/webseminars. Thank you, everyone, for your participation today, and we look forward to seeing you again soon.